All right, the last topic that I want to talk about as far as counting is concerned is permutations and combinations. And then once we've done that, we can move on and talk about probability. Just to give you kind of a brief sort of vision of where we're headed, the probability of a particular event occurring is the number of ways that that event could occur divided by the total number of possible events, period. And so you can see why being able to count up the number of ways something can happen is important. And so that's why we've been talking about counting. This lecture we're going to talk about, like I said, permutations and combinations. So in lecture 21 we used tree diagrams to count the number of ways to perform a task. In lecture 22 we saw that the fundamental counting principle was a shortcut for doing the same thing. In this lecture we're going to learn about two more shortcuts for counting, that's permutations and combinations. And those are both shortcuts for counting the number of ways to select R items from N items without repetition, or in other words, without replacement. Okay, those mean the same thing. Now, the reason we're not worried about how to count when repetition is allowed is that we already have a shortcut for that, and it's called exponents, right? So to give you just an example of that, airport codes like LAX, International Airport, right? Airport codes consist of 3 letters, LAX, right? The letters may be repeated. So, for example, I think Fort Lauderdale International Airport is FLL. So you can have the same letter repeated, okay? The question is, how many airport codes are possible? Use exponents to write your answer. So I'm actually going to start with a slot diagram, okay? Because I need to make 3 choices, right? I need to choose 3 letters to form my airport code. And the question is, how many letters do I have to choose the first letter in my code? So how many options are there? Well, there are 26 letters in the English alphabet. So there are 26 possibilities for the first letter. And since letters can be repeated, I still have 26 letters left over for the second letter in my code, and then I'll still have 26 letters left over for the third letter in my code. Now, 26 times 26 times 26 is just 26 cubed, right? It's 26 to the third power, right? If you're interested, 26 to the third power is 17,576. But we were asked to use exponents to write our answer. Anyway, so the moral of the story is, if repetition is allowed, then counting is not difficult, right? You can just use exponents. You can say, well, I had 3 letters and 26 possibilities for each letter, so it's just 26 to the third power. Boom, right? But now imagine that you couldn't reuse the same letter twice in an airport code. So imagine, repetition is not allowed, right? So repetition is not allowed. Okay, well, if that's the case, then again, we have to choose 3 letters for our airport code. We would have 26 possibilities for the first letter, but then because repetition is not allowed, we would only have 25 options for the second letter in the code, and then 24 options for the third letter in the code. 26 times 25 times 24. That's 15,600. Now, we don't have, or we actually do have a shortcut way to write this thing down, but you may or may not be familiar with it, so we're going to introduce it. That said, you may wonder, well, why do we really need a shortcut? It's not that much work to just write out 26 times 25 times 24. And you're right, because we only had to choose 3 letters. But imagine that we needed to choose 20 letters, right? So for the previous scenario, it doesn't seem like we really need a shortcut. It's just 3 letters. But what if the airport codes consisted of 20 letters, right? It would be very tedious to write out 26 times 25 times 24 times 22 times 22 times 21 times 20 times 19, and then also, where would you stop, right? When would you stop? At what number do you stop, right? You'd have to write out 20 little slots. I mean, so that's tedious, right? So we're going to write out a shortcut way to think about this. So for counting with repetition, counting without repetition, we introduce the following notation. Okay, so the symbol n with that little exclamation point, we read that n factorial. So that exclamation point is really a factorial. So n factorial is defined as follows. N factorial is n times n minus 1 times n minus 2 and so forth all the way down to 1, right? And then just we define 0 factorial to be 1, and 1 factorial is also 1. So let me give you an example of how these things work. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. That's what the factorial means. Okay? So you start with the number, and then you multiply by 1 less than it, and then 2 less than it, and then 3 less than it, until you get all the way down to 1. And we can punch that into our calculator. 6 times 5 times 4 times 3 times 2 times 1 is 720. Okay. What about 8 minus 3 factorial? Now be careful. You might be tempted to distribute the factorial and call this 8 factorial minus 3 factorial. And I'll just warn you right now that this is not equal to 8 factorial minus 3 factorial. The factorial does not distribute nicely. What it is equal to is this. 8 minus 3 factorial equals, well, 8 minus 3 is 5. So that equals 5 factorial, right? Which would be 5 times 4 times 3 times 2 times 1. Which is, let's see if we can do it on our heads, 20, 60, 120. Okay? What about 9 factorial divided by 5 factorial? Well, that would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. And notice we get a bunch of things that cancel, right? The 5s cancel, the 4s, the 3s, the 2s, and the 1s. They all cancel. So this just comes out to 9 times 8 times 7 times 6. Okay? 9 times 8 times 7 times 6 is 3,024. Okay? One more. We'll do 8 factorial divided by 5 factorial times 3 factorial. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. Okay, now here we get a bunch of cancellations as well. 5 cancels 5, 4 cancels 4, 3 cancels 3, 2 cancels 2, 1 cancels 1. What about these ones? Well, notice that 3 times 2 is 6. So together, well, 3 times 2 times 1 is 6 for that matter. So together, those three things will cancel to 6. So really, this just ends up being 8 times 7, which is 56. 8 times 7, not 8.7. Anyway, so that's how factorials work. Okay. Now here's how factorials are useful when it comes to counting. Okay. So a permutation is an ordering of distinct objects. If we select R objects from a set of N objects and arrange them in order, this is called a permutation of N objects taken R at a time. The number of permutations of N objects taken R at a time is denoted by P of NR or N permute R. Some books use this symbol, some books use this symbol. We'll use this symbol for this class. Okay. A lot of calculators have a permutation button on them. Sometimes they look like this, and sometimes they look like that. Okay, but anyway, here's how you count the number of permutations. So it turns out the number of permutations of n objects taken r at a time is n factorial divided by n minus r factorial. So let me run you through a few examples using that formula. So example 3a says, how many permutations are there of the letters A, B, C, and D? Write the answer using P of nr notation. Okay. So how many permutations are there of the letters A, B, C, and D? Well, we have 4 objects to choose from, and we want to choose all 4 of them, but just possibly in different orders. So we would write this as P of 4, 4. Right? N equals 4 and R equals 4. So that's going to be 4 factorial divided by 4 minus 4 factorial. Or in other words, 4 factorial divided by 0 factorial. Or in other words, 4 times 3 times 2 times 1 divided by 0 factorial. Remember, we defined 0 factorial to be 1 on the previous page. Okay, so we can do that in our head. So it's 12 times 2 is 24. So there are 24 different ways that you can arrange A, B, C, D, right? You could have A, B, C, D, A, B, D, C, right? A, C, B, D, A, C, D, B, right? And so forth, right? I'm not going to list them all, but yeah, there are 24 different ways to list them. Next example. How many permutations are there of the letters A, B, C, D, E, F, G if we take the letters 3 at a time? So this time there are 1, 2, 3, 4, 5, 6, 7 letters. And we're going to choose 3 of them, right? So we're not going to rearrange all 7 of them. We're just going to rearrange 3 of them at a time. So this is going to be P of 7 permute 3. Okay? So N is 7, R is 3. Right? So that's going to be N factorial, right? So 7 factorial divided by N minus R factorial, right? So 7 minus 3 factorial. So that comes out to 7 factorial divided by 4 factorial. Or in other words, 7 times 3 times, or 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Those things cancel those things. So this is 7 times 6 times 5. Whoops, 7 times 6 times 5. It's 210. Okay. Here's another example. In how many ways can horses in a 10-horse race finish first, second, and third? Okay, so there are 10 horses, so we have 10 horses to choose from, and we need to pick the top 3, so we need to pick 3 of them. So it's going to be 10 permute 3, right? We're going to have 10 permute 3. And we know it's a permutation because we're going to arrange them in order, right? Like the horse we choose first is the horse that comes in first place, and the horse we choose second is the one that comes in second place, and so forth, right? So if you had like Seabiscuit and Secretariat, that's a different thing than Secretariat and Seabiscuit, right? Those are the only horse names I know. Anyway, so it's going to be 10 permute 3. So this is going to be 10 factorial divided by 10 minus 3 factorial. So that's 10 times 9 times 8 times 7 times 6 and so forth all the way down to 1. Divided by 10 minus 3 is really 7 factorial, right? So that's 7 times 6 and so forth all the way down to 1. So I put the dot dot dots because I know that this is going to cancel that and just leave me with 10 times 9 times 8 9 times 8 is 72, times 10 would be 720. Different possibilities, right? Okay. One more example, and then we'll talk about combinations, right? So this one says, a 12-person community theater group produces a yearly musical. Club members select one person from the group to direct the play, a second to supervise the play, and a third to handle publicity, tickets, and other administrative details. In how many ways can the group fill these positions? Okay. So there's 12 people. We need to choose 3 of them, one to direct, one to supervise, one for publicity. So this is going to be 12 permute 3. Okay? So that's 12 factorial divided by 12 minus 3 factorial. So that's 12 factorial over 9 factorial. So 12 times 10 times 12 times 11, right? 12 times 11 times 10 times 9 times 8 and so forth, divided by 9 factorial. And those will cancel those. So we'll get 12 times 11 times 10. So 12 times 11 times 10 is 1,320. Okay, so hold on a second. Okay, so that's how permutations work. Let's take a look at combinations now, right? So with permutations, the order is important, right? So as we said with like the horse race example, Secretariat and Seabiscuit is considered a different outcome than Seabiscuit and Secretariat. But order isn't always important. Not every scenario really distinguishes between the order. For example, a pepperoni and olive pizza is the same thing as an olive and pepperoni pizza, right? So if you were counting the number of possible pizza combinations given a certain set of toppings, the order would not matter. And when the order doesn't matter, then that's a counting problem called a combination, all right? So if we choose R objects from a set of N objects, we say that we are forming a combination of N objects taken R at a time. The notation C of NR, or N choose R, or N choose R, denotes the number of such combinations. So again, different ways to denote combinations. We'll stick with this first one, C of NR. Okay? And as it turns out, the number of combinations of N items choosing R at a time is N factorial divided by R factorial times N minus R factorial. This is really similar looking to the permutation formula, which was N factorial divided by N minus R factorial. Here we just have an additional R factorial down here in the denominator because the order doesn't matter, and so we need to divide through by the different number of ways to arrange the R objects because the order doesn't matter. So that's why that extra R is there compared to this one. Okay, so let me give you a couple examples, and then we'll compare and contrast combinations and permutations in a little bit more detail. So this first one says, how many groups of 3 pictures from a set of 5 can you select to make a custom collage for your Facebook cover? I don't even know what they're talking about. I'm not on Facebook, but whatever. It doesn't matter, because the question is, how many groups of 3 pictures from a set of 5 can you select? Okay, so the order doesn't matter, right? We're going to select 3 pictures from a set of 5 pictures. So this is going to be C of 5, choose 3. Okay, so that's going to be 5 factorial divided by 3 factorial times 5 minus 3 factorial. Okay, so that comes out to 5 factorial over 3 factorial times 2 factorial. That's 5 times 4 times 3 times 2 times 1 divided by 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. So the 3 times 2 times 1 cancels that, 3 times 2 times 1. 2 times 1 is 2, and 2 goes into 4. 2 goes into 4 and leaves 2 in its place, right? So, so this really comes out to 5 times 2. Which is 10. Okay? So that's that. If you have 5 pictures and you want to just choose 3 of them, and the order doesn't matter, then there are 10 ways you can do it. Okay? And it might be nice for you to like actually sit down and fiddle around with this and figure out what the 10 different combinations are so that you can kind of convince yourself of this. But anyway, here's another question. In how many ways can you select a 4-person committee from a set of 10 people? Okay, so we're going to choose from a set of 10 people, and we need to select 4 people to serve on the committee. And the order doesn't matter because the people chosen are just going to be committee members. It's not like the first person chosen is going to be the president of the committee or something. It's just you're choosing 4 people to be on the committee. So the order isn't important here, so it's a combination problem. So from 10 people, we're going to choose 4 of them. That's going to be 10 factorial divided by 4 factorial times 10 minus 4 factorial. So that comes out to 10 factorial over 4 factorial times 6 factorial. So that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1. Well, that cancels that, right? Oh, the rest of them are a little bit harder, but here's what I can do. So I know that 4 times 2 is 8. So the 4 and the 2 together down here cancel the 8 up there. And then I also know that 3, maybe I'll use a different color, but I know that 3 times 1 is 3, and 3 goes into 9 and leaves a 3 in its place. So what we're left with at the end of the day is 10 times 3 times 7, right? We're left with this number, and this number. So 7 times 3 is 21, times 10 is 210. So that's the number of combinations. Okay? That's the number of a 4-person committee that we can take from a set of 10 people. Okay, so that's how combinations work. Now let's compare and contrast the techniques that we've discussed so far in this lecture. So if repetition is allowed, we're just going to use an exponent. This was like example 1 with the airport codes. Okay. If repetition is not allowed, then we're going to use a permutation or a combination. Okay. We'll use a permutation if the order matters. So if AB is considered different from BA, then we use a permutation. We're going to use a combination if the order doesn't matter. So if AB is equivalent to BA, then you use a combination for that. So let's look at another set of examples. So let's say you want to form a committee by choosing 3 people from a group of 20 people. How many committees are possible? Well, the order doesn't matter because the 3 people that you choose to be on the committee are just committee members, right? It's not like one of them is the president, the next is the vice president, or whatever. They all have equal standing. And so if you choose Bob first and Sally second, that's the same situation as if you chose Sally first and Bob second. So the order doesn't matter. And so you're going to use a combination, right? Combination. Now, you have 20 people to choose from. And you're going to choose 3 people to be on your committee. Okay? So that's going to be 20 factorial divided by 3 factorial times 20 minus 3 factorial. So that's 20 factorial divided by 3 factorial times 17 factorial. Okay, so that's 20 times 19 times 18 times 17 times 16 and so forth, all the way down to 1. 3 factorial is 3 times 2 times 1. And then 17 factorial is 17 times 16 and so forth, all the way down to 1. So clearly, the 17 factorial here is going to cancel all of this stuff up there. And then I know that 3 times 2 times 1 is 6, and 6 goes into 18 3 times. So at the end of the day, this is 20 times 19 times 3. Which comes out to 1140. So 1140. Okay. Next part. You want to choose 3 people from a group of 20 people to do some chores. The same person could be chosen multiple times. How many ways can you assign the chores to be done? So the same person could be chosen to do all 3 chores, or you could have a person do 2 of the chores and then a different person do 1 chore or whatever, right? But the same person could be chosen multiple times. So so repetition is allowed, right? Since repetition is allowed, you're just going to use exponents, right? So you need to choose 3 people. If you imagine doing this with a slot diagram, it would look like this, right? You need to choose 3 people to do chores. You have 20 people to choose from for the first chore, 20 people to choose from for the second chore, and then 20 people to choose from for the third chore because repetition is allowed. So in other words, this is 20 cubed. How much is that? That's 8,000. Okay, so 8,000 possibilities. All right. Okay, so this was an exponent problem because repetition was allowed. So it's an exponent problem because repetition is allowed. The part A was a combination problem because repetition was not allowed, right? It didn't make sense for Bob to serve in 2 positions on the committee, right? So repetition is not allowed, and order doesn't matter. Choosing Bob first and Sally second is the same thing as choosing Sally first and Bob second, right? Okay, let's look at the last one. So it says, you want to choose a president, vice president, and secretary from a group of 20 people. How many leadership structures are possible? Okay. So first of all, repetition is not allowed here. It doesn't make sense to choose the same person to serve as the president and as the vice president, right? So you can't have repetition. So automatically we know that, okay, repetition is not allowed, so we're not going to use exponents. This is either going to be a combination or a permutation. Now, how do we choose whether it's a combination or a permutation? We ask ourselves, does the order matter? And the answer to the question is yes, because the first person you choose is going to be the president, the second person you choose is going to be the vice president, and so forth, right? So the order matters, so that makes this a permutation problem, okay? We have 20 people to choose from, and we're going to choose 3 of them to serve as president, vice president, and secretary. So that's going to be 20 factorial divided by 20 minus 3 factorial. So that's 20 factorial divided by 17 factorial. So that's 20 times 19 times 18 times 17 times 16 and so forth, divided by 17 times 16 and so forth. That's going to cancel that. You're left with 20 times 19 times 18, which comes out to 6,840. Okay, but this one was a permutation problem because repetition is not allowed, and order matters here. Okay, so there you go, back to back to back. You've got 3 different examples. In all 3 cases, you're choosing 3 people out of a group of 20 people. But in part B, repetition is allowed. In part A, repetition is not allowed, but order doesn't matter. And then in part C, repetition is not allowed and order does matter. Okay? And so part A is a combination problem, part B is an exponent problem, and part C is a permutation problem. Okay. The last example I want to walk you through in this section just shows you that sometimes you have to do different combinations of these things in order to get the ultimate answer you're looking for. So here's an example. It says, Student Services is selecting 2 men and 2 women to attend a leadership conference. If 10 men and 12 women are qualified for the conference, in how many ways can management make its decision? Okay. Now it might be tempting to say, well, 2 men and 2 women, so there's 4 people, and then 10 men and 12 women, so 22 people, right? So they're just going to choose 4 people out of a set of 22 people, right? It might be tempting to say that, but the Student Services, for whatever reason, is being very specific. They want 2 men and 2 women, okay? And so in order to ensure that that happens, we actually need to select the men out of the pool of men that we have to choose from, and then we need to select the women out of the pool of women that we have to choose from. Okay? So we actually have to make 2 choices here. We have to choose the men, and we have to choose the women. And by the way, it doesn't matter. It doesn't matter which order you do it in. So you could choose the women first and then choose the men. Anyway, so okay, so I'm going to choose the men first. So I'm going to do a little slot diagram here. All right. So this is going to be for the men, and this is going to be for the women. Okay. Now, how many ways can we choose the 2 men that we're going to send to the conference? Well, we're going to select 2 men out of a pool of 10 men. It doesn't say anything about like a ranking system, so it's not like the first person chosen is going to be, president of whatever. It's just they're going to send these 2 people to the conference. So the order in which they're chosen doesn't matter. If you choose Bob and then Tom, it's the same thing as choosing Tom and then Bob, right? It's still the same set of 2 men that you're sending to the conference. So the order doesn't matter. Repetition is not allowed because you can't choose Bob twice, right? You have to choose 2 different men, okay? So repetition is not allowed, so automatically we know it's either a combination or a permutation, not an exponent. And the order does not matter, so that means it's got to be a combination, right? This is going to be a combination. Out of the 10 men that we have available to us, we need to choose 2 of them to go to the conference, okay? Now for the women, you're going to go through a similar line of reasoning, right? It doesn't matter if you choose Jill and then Sally. That's the same thing as choosing Sally and then Jill. So the order doesn't matter, and repetition is not allowed. So this must be a combination problem. And you have 12 women to choose from, you need to choose 2 of them to send to the conference. Okay, so that's how you would set up this problem. Now, for this one, it's going to be 10 factorial divided by 2 factorial times 10 minus 2 factorial. And then for this one, it's going to be 12 factorial divided by 2 factorial times 12 minus 2 factorial. So that's 10 factorial divided by 2 factorial times 8 factorial times 12 factorial divided by 2 factorial times 10 factorial. Okay. So that's 10 times 9 times 8 factorial, I'm just going to say. The 8 factorial will take us all the way down. And then 2 factorial is just 2 times 1. Okay. And then this is going to be 12 times 11 times 10 factorial. 2 factorial is 2 times 1. I'm running out of space, but anyway, these will cancel. The 2 here cancels the 2 there and leaves a 5. These cancel. The 2 there cancels the 2 there and leaves a 6. So we're left with 5 times 9, which is 45. And here we're left with 6 times 11, which is 66. And 45 times 66 is 2,970 different possible ways that you could select the people to send to the conference. Okay, so that's that. That's all I have to say about combinations and permutations, and that'll do it for our section on counting. Okay, so next week we'll talk about probability.